There are multiple ways to define what is an acid and what is a base. The Arrhenius definition is one that we usually teach first. It's very simple. By this definition, an acid is a substance that produces hydrogen ions in aqueous solution. If you put something into water and because of that there come to be hydrogen ions in the water, it's considered an acid. A base is a substance that produces hydroxide ions in aqueous solution. So here's an example. HCl is an acid. By this definition, it is an acid because it produces hydrogen ions in solution. I've got a picture over here. We put HCl in here, and it forms hydrogen ions and chloride ions. And here's a little chemical equation down here. Is HCl ionic? No, it's not. It's covalent. It says so right there. It's a covalent compound. But when you put this covalent compound into water, it ionizes completely. And so that's why it's sometimes a little confusing. Is it ionic or not? Well, I know it makes ions, but if you look at the bond between the hydrogen and the chlorine, it is not an ionic bond. It also follows the rule that we learned that ionic compounds have a metal and a nonmetal in them. And even though hydrogen likes to hang over with the metals on the periodic table, he's not a metal, is he? He's a gas, a nonmetal. So you put HCl into water and it forms hydrogen ions and chloride ions. I didn't realize I was going to be writing in red, but there we go. So this has two names. Hydrogen chloride would be its name as a covalent compound. And that's what we call it when it's pure or in the gas state. When we put it into water, so this would be HCl, and if we put it into water, then it is hydrochloric acid. That's when we put AQ after it. A solution of hydrogen chloride is hydrochloric acid.
I have a question.
Yes?
The fact that it deionizes like that, is that because of the difference in electronegativity between hydrogen and chloride, or is it some other reason?
That's a good question. Why does it ionize in solution? I believe it has to do with the forces of attraction between water and the components of the hydrogen chloride, that water is able to solvate the HCl much in the same way it does with an ionic compound. Hydrogen ions are very reactive. What is a hydrogen ion? It's just a proton. A hydrogen atom is one proton and one electron. You take the electron away, what do you have left? A proton. So here we have a naked little proton swimming around. It's not going to be very happy by itself. It's going to be very, very reactive. So here we've got this proton, and here's water, and water has two lone pairs. If this little hydrogen ion comes over here, it can form a coordinate covalent bond with oxygen and get an octet. And that doesn't really upset the oxygen too much. The oxygen still has a full valence shell. And now we have an overall positive charge on the whole thing. And so the hydrogen will bond to the water. There are other species. This one is called the hydronium ion, H3O+. You can have similar things with different numbers of water molecules. You can have H2O3 or 2. Those exist. So chemists tend to use the H plus and H3O+ interchangeably because sometimes one's more convenient and other times another one is more convenient. So I haven't talked to you guys about chemistry land yet, have I? It's the happiest place on earth. It's like Disneyland. This is my fantasy world where, you know, atoms have personalities and things. So in chemistry land, the way I think of this is a hydrogen ion is a very little guy, right? He's like a 3-month-old baby. Do 3-month-old babies go out into the neighborhood and play by themselves? No. Do they go outside? Only when someone's carrying them, right? They're too small to be out by themselves. A hydrogen ion is too small to be out by himself. So if he finds himself alone, a water molecule is going to come and pick him up very quickly. Because if you were out for a walk and you saw a newborn baby lying on the sidewalk, would you just say, oh, and walk past? No. You'd pick it up and try to find the person that it belongs to, right? Or take it to the police station or something, right? I hope you would. So that's how I see a hydrogen ion. Little tiny guy, can't be out by himself. And so when we write H plus in a chemical equation, instead of H3O plus, we have to remember, oh yeah, he's not there by himself. He's actually being held by a water molecule. And it's really the hydronium ion. But it just gets really tedious sometimes if we have to write that out all the time, and then we have to have a water molecule on the other side, and so it's a little shortcut that we do. So sodium hydroxide was the first base in that table. Sodium hydroxide is a base by the Arrhenius definition because it produces hydroxide ions in solution. Now, sodium hydroxide is an ionic compound formed of sodium ions and hydroxide ions. And so when it is dissolved in water, it dissociates. Let me backtrack a little bit. HCl is a covalent compound. It ionizes. It did not have ions before. It forms ions when it comes in contact with water. We use a different word for the ionic compound. We say it dissociates into its ions. Solid sodium hydroxide contains ions. When you put it in water, they just separate. We're not forming ions, we're just separating them. So it dissociates. There's a picture of that. So we put it into water and it forms hydroxide ions. Arrhenius says that's a base. Caught myself. It's a base. And then we observe that acids and bases combine to form water. So they're going to neutralize each other. So here's an acid and here's the base. And when those two guys get together, they form a water molecule. The state symbol for water is a liquid. We don't say that it's aqueous because water can't really be dissolved in itself. Any questions about Arrhenius?
There's heat involved with that interconnection with the right?
There often is heat involved, yes. But we're not talking about that right now. Yeah, if you mix an acid and a base, it generally creates a warm solution, so there is heat given off.
So is everything either an acid or a base?
No.
So it can be neutral as well?
Yes, and in fact, I would say most compounds are neither. Most are neither. So another definition is the Bronsted Lowry definition. And this is good because it applies in more situations than the Arrhenius definition. The Arrhenius definition only applies to aqueous solutions. What if you have a non-aqueous solution, like in organic chemistry, and you're doing something in ethanol? Is there no acid-base chemistry? No, there's still acid-base chemistry even if water isn't there. So this applies to things like that. This focuses on the transfer of hydrogen ions. And remember, we determined that a hydrogen ion is a proton. So proton and hydrogen ion mean exactly the same thing. An acid is defined as a proton donor. A base is a proton acceptor. So sometimes that can be a little hard to remember. In chemistry land, the person who accepts the proton, who's like the baby, is the babysitter. The base is the babysitter. They both start with B. There's a little picture into my twisted mind. So we would say by Bronsted Lowry definition, HCl is an acid because it donates a proton to water. So we would write it this way: HCl aqueous plus water forms H3O plus and chloride minus. And so this hydrogen ion, this proton, has been donated by the HCl to the water molecule. And this is the result. Any questions? Bronsted Lowry definition also applies to bases such as NH3 that do not have OH minus ions in them. Many of the bases are metal hydroxides, but there are other things that are also bases that do not contain hydroxide ions. So ammonia is a base because it accepts a proton from water. Put ammonia in water and it will accept a proton, becoming the ammonium ion, and after the water donates the proton, it becomes a hydroxide ion. So with the Bronsted Lowry definition, acids and bases always occur together. Because if someone's going to accept a proton, someone else must be donating a proton. Protons do not appear out of nowhere, just like babies don't appear out of nowhere. So in this situation, this is the base because it is accepting a proton. And here, this is the acid because it's donating the proton to the water. Can't remember where the slides are going next. Okay. Actually, I want to go back to that. Finish this out a little bit. So, if this is the base that's donating a proton, what's the acid that's accepting the proton? I'm sorry. NH3, ammonia is the base that's accepting the proton. Who's donating it?
Water.
Water. So that makes water an acid. What do you
By
know?
definition.
Yeah. Well, what about down here? This is an acid. It's donating a proton. Who does it donate it to?
Water.
Water. So water's acting as a base. So water can act as an acid or a base. And we have a word for that. It's called amphoteric.
No. Okay.
Where do amphibians live?
Water and land.
Water and land. Amphoteric species can be acids or bases. You can't be both at the same time. You know, a frog can't be in the water and on land at the same time. You're one or the other. But it can be either. So when we look at this and reverse this reaction, so we were looking at ammonia plus water. What if we flip it around and now we have ammonium ion and hydroxide ion? Which one is the acid in the reactants? Okay, so the ammonium ion is the acid because it's going to donate the proton, and who's the base? The base is the hydroxide ion. So we look at what does this become? Well, it becomes NH3. It did that by losing H+. The OH minus becomes H2O by gaining H+. When this was reversed, this was the base, and that was the acid, right? When we were looking at ammonia plus water, the water accepted a proton, the water donated a proton to the ammonia. And so we call this, I'll get to that. It's on the next slide. We call it a conjugate base. But the substance that was the base, this was the base, now it's the acid. And so they go back and forth. And these are called conjugate acid-base pairs. So the conjugate acid is a base that has accepted, I'm losing my words. I'm going to start that one over. I think it was okay, but I'm going to start it over anyway. A conjugate acid is any base that has added a proton, accepted a proton.
And it has to have a plus charge?
It does not have to have a plus charge, and we'll see that. A conjugate base is an acid that has donated its proton. So when an acid performs its function as an acid and donates its proton, it becomes a base, because it could then take that proton back. It's like two people handing a baby back and forth. If I have the baby, I'm the acid. If I give you the baby now, you have acted as the base by taking the baby. You're the babysitter. But now you have the baby, and you could donate that proton to something else, and so you're now the conjugate acid. Does that make sense? It's really important that you understand that they're just so closely related. It's just a proton. Where's the proton? So conjugate acid-base pairs are two substances that are related to each other by the transfer of a proton. So when you look at two species to see, is this a conjugate acid-base pair, the only difference is that one has an H plus and the other doesn't. So if we look at these two guys, NH3 and NH4 plus, this has one more H plus than this one does. This is the conjugate acid because it could donate that proton. This is the base. Water, amphoteric, it can act as an acid or a base. Here it's acting as an acid. It donates the proton, loses it. Now we've got pointer problems. Now we've got OH minus, which is the conjugate base. So if we look at water instead of, here it was the acid, what if we look at water as the base? What's the conjugate acid? Water is the base. What's the conjugate acid? H3O plus. So that's the conjugate acid. So the only difference between these is an H plus. The acid has it, the base doesn't. Any questions? Let's look at an example. In each reaction, identify the Bronsted Lowry acid, the Bronsted Lowry base, the conjugate acid, and the conjugate base. So I'm going to look at this guy, C5H5N, and there's going to be somebody over here that's real similar to him. That would be this guy. And so I'm going to see, well, what does this guy do? He's accepting an H plus. See, now here he's got the H plus, there he doesn't. Now he does, now he doesn't. The base accepts. So over here, this is the base. It's going to accept the hydrogen ion. That makes this guy over here the conjugate base. I'm sorry, thank you. I was testing you. Conjugate acid. If this is the base, what's the acid? The water. And we can confirm that by looking at what does the water become? It becomes hydroxide. It's missing an H plus. So this is the acid. And then over here, this is the conjugate base. That make sense? How about down here? So HNO3 is acting as what?
The acid.
The acid, because here it's got a hydrogen ion and here it has donated it. So that's the acid. I'll do this one in a little bit of a different order. If that's the acid, the other one, when there's only two reactants, has to be the base. And we see that the H2O is accepting, went too far, accepting the hydrogen ion. So this one is the conjugate, what?
Acid.
Acid. And this one is the conjugate base.
Does it really matter which side is going to be labeled as conjugate?
Very good question. Does it matter which side is labeled as conjugate? Not really. We usually label the left side, the reactants, as the acid and the base, and we usually label the products as the conjugate acid and base. Most of these, you'll notice, are going to be equilibria, and so they could go either way. And we can write the equation in either direction as well. We're usually going to write it so that the forward direction precedes more than the reverse direction, but it doesn't have to be that way. Any questions?
You said the book has an example, you write where the H2SO4 aqueous plus H2OL liquid, it's just going in one direction.
Yeah, we'll learn about that. There are strong acids and weak acids. And strong acids like HCl ionize completely, and so you're not going to see as much of an equilibrium with them. And the weak acids only go partially, and so those are usually written with equilibria arrows.